Thank you very much for the welcome, and it's my pleasure to be the last speaker, and promise that I'll be on time, which is very important, especially when it's Friday. So today, I guess I was placed last because we want to contrast all the talk about asphalt the last couple of days with concrete. So today I'll hope to give a good overview of some strategies that can be used to design overlays of existing roadways with concrete. And especially we'll focus a little bit on use of fibers to improve their performance. And this research that we've been doing over the last 10 years is kind of a summary of what we found to work, different types of overlays, and some guidelines that have been developed. And I've also have a lot of references in my presentations that if you're interested, you can read that are publicly available if you just Google the documents I'll show. So we'll have talk about design and also use of fibers. This bottom figure here is a X-ray tomography of fibers inside of concrete and shows the distribution. And we found that, especially for the overlays that I'll talk about that seem to be most applicable to Costa Rica, would be thin overlays with fibers. As I said, we've done a lot of work for our state government and other organizations related to overlays for concrete over the last 10 years. So this is kind of my presentation outline, and we'll go through a little bit of some of the design guides. The main thing is to understand what type of overlays I should use and when are these overlays applicable. We'll spend a lot of time on bonded concrete overlays, on asphalt, which is, from what I observe here in my brief stay so far, is most of your roads are asphalt, and so you can place these on top of the asphalt after you mill them. Also a little bit on unbonded overlays, which again have a certain application depending on the traffic. And then we'll intersperse some things on materials and jointing and construction. So kind of our objective designing overlays are providing a design that gives the agency or the owner the life that they want. So if you want, we design pavements for a life of 10 years, 15, 20, 30. So you have to define what kind of life do you want to achieve with your overlay. And for certain conditions, you may only want a 10-year design. In other conditions, you may want a 30-year design if it's a high-volume road, one of your highways or your arterials. So kind of the things you want to think about as you're designing an overlay is we need to know the condition of the roadway. That's very important. A lot of overlays fail when you try them new because people don't adequately evaluate what you have and whether, when I put an overlay, will it work. The traffic is very important, obviously, especially the amount of trucks, and that goes for any type of pavement design. Another big issue is what type of layers do I have and what material property could I use on my concrete overlay. And one of the more important things we have to define is this interface condition. Is the concrete bonded or not bonded to the existing pavement? So that has to be defined, and that drives your decision on what type of overlay you're going to use. We have to also, as we do our design, select the right slab size or the slight slab geometry if we want to have adequate performance. And the local climate has a huge role on performance. We've seen that for a variety of overlays, and I would suspect here with a lot of rain, you have to make sure you get good bond because moisture sensitivity is a problem. Now, keep in mind, we can do overlays. I'm not talking about overlays just concrete on concrete. I'm talking about overlays concrete on asphalt or concrete on top of asphalt, which was placed on top of concrete. So there's a lot of options where we can have overlays for concrete. Maybe some of you have heard of this term white topping. It's used rather loosely. And in general, it doesn't really tell you too much about an overlay except that you're putting concrete on top of asphalt. That's all it really means, to me at least. Some people use it kind of incorrectly. So typically, this is why you call it white topping, because it's white on black. Of course, this is traditionally done when you have a new concrete and you put asphalt. So What's more important is what's the interface condition here between the concrete and asphalt. So white topping doesn't tell me if it's bonded or not bonded. I have to know what that is because my structural design calculations depend on that. So this is a little better comparison. It's still not exactly correct, but traditionally we've designed what people call white topping, which I define as unbonded. This interface here is unbonded. These are thicker slabs, and this has been around for a number of years, not exclusively used in many places, but people have tried this. More recently, in the past 20 years, when this technology for thin overlays began, we need to have a bond here, okay? So we have to have some adhesion to the asphalt. And concrete and asphalt don't bond extremely well, so we have to clean it. We have to mill the surface to promote as much bond as possible. The other feature here is shorter panels or shorter slabs. These are very short, less than 1.8 meter. These tend to be a lot larger in terms of the slab size. So if we look at all the available overlays for concrete, we just talked about concrete on asphalt here, no bond. This is a bonded system, okay? And then we have unbonded systems here where we put a separation layer, like such as asphalt, in between because this condition here is not very good. And finally, this is the least common you'll find. It's very difficult to build, but at times you may want to do this, maybe on an airport for a variety of reasons. But then you have a bonded concrete to an original concrete. And I'll go through each one of these in varying details. Mostly we'll cover this one because it has the largest potential, at least in the US, it's growing quite rapidly because it can be used on lower to medium volume roads, which is most of your road network. So if we look at all the categories kind of organized in this flow chart, we have, you can think of, something happened. Okay. Think of bonded overlays tend to produce thinner structural designs because I'm bonding one material to another material, so they're sharing the stressless. And unbonded overlay, generally, you discount the contribution of the underlying layers. And you can also think of unbonded overlays, the existing roadway, whether it's asphalt or concrete, is in a poorer condition. So I can't use its capacity as much, whereas on a bonded overlay, generally, I still have some structural contributions with the existing pavement. So let's think about just briefly the difference here in terms of stresses or strains. If I have a bonded system here and I load it, I'm essentially here, this interface is sharing the load. This is essentially stuck together, and the strains across that interface, the strains across this interface are equal. So I share the stresses. In fact, I tend to have very low stresses at the bottom of the concrete when I bond, so the top stresses are usually critical. In an unbonded system, you have a slip here, so the shear strains or shear stresses here aren't the same, and I have compression and tension at the top and bottom, as well as in the asphalt, the same behavior. So these produce thicker slabs when you design them than when you bond them. So one would prefer bonded overlays, except that in most conditions, we let our pavements deteriorate to a point where we have to choose this option. So one thing we like with the bonded system, at least for asphalt, concrete can be placed on probably a more deteriorated asphalt pavement than if it's a deteriorated concrete pavement. You really don't want to put concrete on concrete. This is a great guide if you really want to learn in a more slow manner about different types of overlays. I helped write this about 5 years ago, and we're actually re-releasing a new version here by the end of the year. But this gives a good overview of what I've just said in great detail about the different options and why I would use one versus the other. And you can just Google this. This was published by the National Concrete Pavement Technology Center at Iowa State. Again, one thing we want to think about is when we look at bonded, this is existing pavement condition versus time. So we would like to have a bonded system because it actually only requires a thinner slab to be placed. That means we must have fairly good condition of the underlying asphalt or concrete in order to bond to it. As we allow the pavement to deteriorate, then we'll have to choose an unbonded concrete option, which again becomes more expensive, and you have other problems that you have to deal with when you when you have an unbonded system. If you allow too much deterioration, you have to do reconstruction, which is really our most difficult, most expensive, most time-delaying type of rehabilitation technique. Well, if you're thinking you want to try this out, almost every state in the U.S., there's 50 of them, have tried this, so almost 50. So a lot of what I've talked about here has been tried in almost all the states in the U.S. So this is, a lot of the information here isn't new information. Some of it's not that old, less than 10 years old, but it's not something where you feel like you're putting a test section down and you'll be the first to discover if it works or not. Here's my state where I live. Professor El-Kadi and I live about right there. Chicago's right here, and we've tried close to 100 overlays in the past 20 years, so we have a lot of experience. If you really want to get more information, you can go out to this American Concrete Pavement Association website. They actually have a database of about 1,000 different projects that have been done in the U.S. that people have loaded the information up, so you can go and look and check and see what kind of projects have been done, where they've been built, how they performed. This is on their website, and it's a nice web interface. Well, this is a state I live in, and at this point, this is where all the overlays have been done, mostly near urban areas. This is where Chicago area is, where you have about 9 million people. The state that I live in here is about 3 times the size of Costa Rica. It's about 150,000 square kilometers. This also has a fair number of people here. And the rest of the state's very rural, a lot of farms. So it's still being used in rural areas because of the relatively heavy trucks that are used for carrying goods and services to market. Well, there's a fair number of design guides that are available, but not all of them do overlays very well. Some of the ones that I would recommend, and we'll talk briefly about, are probably the ACPA design guide, and they have a web calculator that you can do this on a website now. The old AASHTO method can do overlays. It wouldn't be the best one to choose, but it does do it on some types of overlays. And on airports, you can use some of the Federal Aviation Administration, and that's a free software. The Portland Cement Association has an old overlay guide, but more recently it's been republished and updated by ACPA as Street Pave 12. So these are some design methods you can go out. Some of these are free, some of these cost a little bit of money. We also recently published last year a guide that has great detail on these different design guides I just showed, and when they can be applied, what are the constraints of each design guide for concrete overlay. And again, this can be downloaded off the website, and it goes through each of the applicable existing methods. And we actually have design examples in here, so you can actually go through the calculations as we show them in this design manual. There's a couple key designs. One is the empirical method, which is basically based on the AASHTO method, which probably you're familiar with. It's an effective thickness approach. And the other one that, again, I like to recommend for at least some of the overlay types is the mechanistic empirical procedure. It's now called, it used to be called MEPDG. Now it's called AASHTO Pavement ME as of a couple of years ago, so they keep changing the name. And this one's probably very good. It's as modern as you can get, but it doesn't apply to all the overlays that we'll talk about today. It only applies to certain ones. This is a shot of the AASHTO Pavement ME software that can do asphalt and concrete overlays for that matter. Unfortunately, this one costs money, and I don't even have a copy. Since it's for this university, they give me a discount. It's $5,000 a year, which I don't think is much of a discount. So let's talk a little bit about bonded overlays. these can be constructed again over concrete, over asphalt, or what we call a composite bonded overlay. And these generally range from 5 to 15 centimeters. Rarely do you see one that's 5 centimeters. It's probably more like 8 or 9 centimeters thick. In all cases, since you want the interface to be bonded, that's the key point. So when you do your design and put your construction specifications together, you have to assure the bond is going to be there. If it's not, these will fail very rapidly. And as I said before, you want to have the condition of the underlying to be fairly good, not extremely poor. Now, what's fair and what's good, that's somewhat subjective, but you can't have an extremely poor existing pavement and expect a bonded overlay to work very effectively. But in general, as we design these, we're trying to restore some of the structural capacity, some of the ride, and in many cases, these bonded overlays are for reasons like rutting of asphalt that has occurred at intersections or bus stops. So that's where the main application began for these. If there's some fatigue cracking, you can do a bonded overlay. If you have a large amount of fatigue cracking, a bonded overlay really doesn't make sense because there's no structural capacity in the asphalt. So you need, the key here, you need minimum support in terms of thickness of the underlying pavement. Most likely it'll be asphalt, and it can't be severely cracked. Some of the failures of bonded concrete overlays of asphalt have been because of inadequate asphalt thickness and a lot of cracking, and they fail in a year. So if you're going to choose a project, make sure it's not the worst asphalt you've ever seen to place a bonded overlay. That won't work. So this is a picture out of that manual. Again, you can have a fair number of distresses and different types of distresses. Generally, if it's a roadway, we mill the surface with a milling machine that grinds down a certain thickness of the asphalt so you can put in an inlay. So it's kind of an overlay, but an inlay is defined as removing some of the asphalt so that you don't have elevation restrictions and you can maintain drainage on your roadway. This gives a good example of what a bonded concrete overlay looks like. Since we want to promote bond, we need to have the slabs shorter. The longer you make your concrete slabs, the more shear stress at the bottom, and you debond the slab from the asphalt. So we cut the slab short in order to reduce the stresses at the interface. We also cut the slab short so that the stresses in the slab due to loading are smaller, okay? So shorter slabs reduce the curling stresses, they reduce the loading stresses. And you can think of many applications in cities, parking lots, bus stops, intersections, and lower volume roads outside the city that these will work very nicely. So those are the applications, and generally these are less than 15 centimeters. Just to give you an example, we did this on our campus about 7 years ago. So this is a parking lot on campus. This would just be a simple example. You can see the condition of this parking lot. And it's mostly passenger cars. Occasionally you get a truck, but not very many. This is about 65 millimeters of asphalt. It's very easy to construct. In fact, you have laborers here. They put up some wood forms. You make sure your forms help the water to drain to your inlets. And you have a crew that actually you don't even need mechanized equipment to do it on a parking lot. And you have to clean the surface very well, of course, because you want this to bond. But this parking lot's very oxidized, so it actually is pretty good to bond to. And actually, one of the other features that we like to use is fibers. So this has about 1.8 kilograms of fibers. We recommend them for all overlays. And this is your final product here. You can see this is about 9 centimeters here, and this asphalt's about 65 millimeters. And your final product, these are 1.2 meter panels. We'll get into the calculations in a second, how we come up with what number to use, what slab size to use, etc. In fact, when I was here 2 days ago, I emailed my student and said, can you take a picture of this, what it looks like today? So this is 2 days ago. He ran over, took a picture of this road, this parking lot 7 years later, and looks good. It's just cars. It's very cost effective for the university to build this because they don't have to hire an engineering firm to do the design. They can just have their crew come out and actually pave this themselves and just make sure the drainage works. There's one other parking lot on campus we did 6 years ago, and this again is basically the same type of design. This is at the Student Health Center. Again, a distressed asphalt that had been there some time, I don't know how many years, has a fair number of distress, but you can easily place this over the top very cheaply, and with the price of asphalt, at least at the time these were done, is when the price of asphalt went up, so you have a very cost competitive option to rehabilitate parking lots. Now, I wouldn't want to say there's no problems ever with these. There's some issues with when you construct these. These are very thin, and you have to deal with these generally in the summer where we live is when they construct them. So you have to do some modifications for hot weather concrete. And that means just making sure you cure it properly. In this case, we had some cracking once on one of the projects because of the wind and the hot temperature. So we just had to adjust our process of the construction. One other problem is mixing the fibers. These are 40 millimeter fibers, which I'll show in a second, but occasionally if the contractor or the material supplier doesn't mix the fibers properly at the plant, you find this later on. Now, it doesn't really cause major problems, but you can see it on the surface, so it kind of looks bad. Overall, though, both these parking lots really have no distress. Again, they don't have any trucks passing them, so one wouldn't expect that. We actually helped, again, put this overlay design for asphalt recently. And so this is a really good, if you're thinking about redoing parking lots and you don't know to use concrete or asphalt, this at least gives you a guide to make some decisions about what you would do and what the cost would be, what the thicknesses would be. Okay, so we're going to talk a little bit about how we go about designing one of these. Again, keep in mind that we're going to have shorter panels, shorter slab sizes, and our slab thicknesses are they have to turn out to be in this range, because if we have too thick of slabs, then this idea of bonding to the asphalt doesn't really make sense. Also, we have to keep in mind that we want to maintain a minimum asphalt thickness. If our asphalt gets too thin, then the concrete's carrying all the stress, and it's not going to be thick enough then. So when we think about load stresses, when we have a bonded system here, when we load at the typical mid-slab edge with our standard load, the stresses are actually supposed to be at the bottom, the tensile stresses, but it turns out it puts a tensile strain at the bottom of the asphalt because these are bonded. So typically we design these for this type of loading here at the joint because the stresses at the top are actually the highest when we look at all the loading positions. So when we do our structural analysis, we do this type of analysis to get top tensile stresses. And therefore, that's why we assume there's a bond. If we assume there's no bond and we design for this axial position, then these slab thicknesses will be much greater, okay? So it kind of gives you a feeling that you have, in terms of the calculation of stresses, if I want to assume no bond, then this is generally my critical location. If I assume there's bond, then this is my critical location. Now, the ACPA had put out a design bulletin. They're the ones that really pushed this technology about 15 years ago, and they have their own design method. They call it white topping, which covers thicker and thinner slabs. And again, it's still probably the best manual on how to design these. They have a bunch of tables like this inside that design manual with the idea I've just shared. But recently we actually took their calculations and put it on a website, and I'll show that in a second. And this is what we call the modified ACPA design. This is at a website that I'll show you in a second, and we actually use it for our state DOT design guide. The AASHTO method for these thin overlays, it actually is not applicable. So you can't actually structurally design with AASHTO 93 or even 2011, okay? So that's one of the things, the limitations on these two new AASHTO methods. They require the slab be 6 inches thick, 15 centimeters, and the slab has to be at least 3 meters long, or you can't use the design method. So you have to go to some other approach. This is a milling machine here. Typically, if you're putting this in a city, you'll probably have to mill the surface so you can keep the curb and gutter in the right location. So you have to mill the surface here. This is a mill machine. And we have a minimum requirement of how much asphalt's left after you mill it. So about 6.5 centimeters. Can you go a little bit lower than that? Probably, but you don't want to get too low because of the variability and thickness of the asphalt. Again, it's important to clean the surface because the bond is the most important part in your assumption of your design. So you can wash it or sweep it, but you just need to get the oil and the dust and debris off the surface. This is just another example that although this looks like it's in pretty bad shape, there's been plenty of bonded overlays placed on pavements like this. So you may have sections that they're not in great shape and you may have to do a patch or something, but when you apply overlays of the nature I'm talking about, you're not expecting these to last 30 years. You're thinking 15 to 20 years as your design life, okay? So when you design concrete pavements, most people think they last forever, but thin overlays are not going to last for 30 years generally. Just like you don't design an asphalt overlay to last 30 years, you're not going to design a concrete overlay that's very thin to last 30 years. Well, anyway, past researchers have developed stress equations to calculate the stresses in the concrete for various asphalt thicknesses, various slab sizes, and these equations are well known. And so when you run the actual design program, this is a mechanistic-based design program, and all these calculations are included. When you're thinking about the structural design, these are the main factors you need to get a handle on. Again, as I said before, the thickness of the asphalt layer, the stiffness of that asphalt layer and its condition, that affects the thickness, how large a slab you want to design, 1.2, 1.8. We don't really go above 1.8 for thin overlays. It's about half your lane width. And whether you're going to use fibers or not. And these are structural fibers that we're going to use. Generally, we make some assumptions on the asphalt. You can't go out and do extensive testing on all the projects because the asphalt stiffness is going to change as a function of time and temperature. And so we generally assume some type of fair condition in our state. If you had a different state, you could change, or a different climate condition here, you'd probably assume a different value. Traffic, you can assume easels or a load spectra analysis. Generally, we use easels, but the design allows you to use a load spectra. So it doesn't really matter how you characterize the traffic. Both the methods work pretty well. And our fatigue algorithm is based on a bunch of laboratory tests that were done over the years. And we basically have a fatigue algorithm that accounts for the stress ratio, the stress in the concrete strength, the probability of failure that you want to have in your design. You want a 50% probability of failure when you think you have those load repetitions, and this is the number of load repetitions to failure. So once we calculate stresses, we know what concrete we're going to use. We calculate the amount of traffic, essentially, that you need or you can have before failure. We also can adjust these. I'm not going to go through all these equations here. We can adjust this for how many cracks are acceptable in your design. So when you design a concrete slab, you ask yourself, well, what's failure? Is it 10% of my slab's cracked? Is it 20? Is it 50? So the engineer can actually decide what failure is. If you're in a parking lot, you can have a lot of slabs cracked, right? I can do 50%. I have slow-moving traffic. It's not a big deal. If I'm on a highway, I'm probably going to have a lot less, like 20%, 15%, because you don't want to very rough ride it with high moving traffic. Okay, now what about fibers? The fibers we've found to be very effective. The fibers we're talking about are what we call structural fibers or macro fibers. They're about 40 millimeters, 50 millimeters long. They can either be steel or polyethylene, polypropylene type materials. And they provide a toughening of the concrete matrix, okay? They don't improve the actual tensile strength of the concrete, but they improve the capacity of the slab when you introduce fibers. So probably most people know of what we call microfibers. These are the very small fibers, about 6 millimeters, and most ready-mix plants actually sell these. And they put them all over the place. But they actually don't provide the structural capacity enhancements that these macro fibers give you, okay? So microfibers are good, but they're really for plastic shrinkage crack control. Macrofibers, we actually can hold cracks together at the kind of micro level such that they never propagate to the surface. So I specify macrofibers, and microfibers are fine, but they're not going to actually give you the crack control that you want for an overlay. And an overlay, once you start getting some cracking, you want to hold it together. So one thing is how do we figure out what fiber to use, how much fiber we want to put in, and we came up, a bunch of people have come up with this standard as kind of a reasonable way of testing a fiber reinforced beam. It's a standard beam actually, but we have to measure the load displacement of this beam and measure that after the peak load also. And this gives us an idea of the toughness of the fiber, or of the fibrous concrete. And we can then look at the quality of the fiber. Now, all fibers are not created equal, unlike all humans, right? So we have to test the fibers. Cheaper fibers in general don't perform as well, so you have to add more of them into the mixture. So you always have a trade-off. You have high quality fibers, but they're more expensive, but you don't need to add as many. So you have to run your tests. You can't trust what the manufacturer always says. Sometimes they're very truthful, sometimes they just want to sell fibers. So this would be typical of a fiber reinforced mix here. You have about the same peak load when you test a beam with whether you have steel or synthetic fibers, but this is what I call the toughness, the post-peak behavior. And you can see that this is steel fiber, and this is another steel, and this is synthetic. They all produce about the same curve, but different volume fractions. So you can see that you have to test the fiber you want to use and make sure it's going to behave the way you want to. But in general, the peak load doesn't change. It's what we call the post-peak load. And I won't go through all the detail here, but generally we calculate what the residual strength is at some deflection level, and we define that as 3 millimeters in the standard. So this gives us an idea of the quality of the fiber in the concrete. One thing about fibers is one fiber may work very well for paving concrete, and it may not work very well for high-strength concrete, and vice versa. So high-strength concrete use shorter fibers, but they don't work as good in paving concrete. So fibers are kind of designed to work for certain applications. So you have to kind of do your research on which are the best fibers to use. Now, this is the important part. I said that when I add fibers to concrete, they don't increase its tensile strength. But when we add fibers and we test a slab, and these are slab tests, so I put fibers in a concrete slab and then I test it, I load it. And it increases the cracking strength of the slab. So if I had a plain concrete slab, which is this blue line here, the peak load here is about a little bit over 100 kilonewtons. When I add fibers, the peak loads are all over 125 kilonewtons. It doesn't matter what fiber type. So although the tensile strength of the concrete doesn't change, as soon as the cracking propagates, the fibers keep the crack closed, and my slab capacity increases. So we actually use this information in the design to make the slab actually thinner than it needs to be, because I realize an increase in the capacity of the slab. So we can design thin overlays and still do it economically with fibers. Now, as the slab gets thicker and thicker, let's say for airports, you have, let's say, 50 centimeters, something like that for your airports. It doesn't make sense economically to add fibers. You have such a large volume of concrete, you're really not getting the benefit. But for thin overlays, it makes a lot of sense. So in our structural design equations, we use the test method and the residual strength to account for the added benefit fibers have in terms of slab capacity. So this is the key point when you add macro fibers into concrete. They actually do benefit you from a thickness design standpoint. And this is just how we incorporate. We put fibers in, and it affects the fatigue life essentially for the concrete by adding this residual strength factor to the strength of the concrete. Well, we have all the equations actually on a spreadsheet. It's not actually that many equations, and I'm actually So if we put all these into a spreadsheet, we can come up with a design method which exists here, and I just wanted to show you some of the sensitivity of a bonded concrete overlay of an asphalt pavement. So this figure here just shows the sensitivity of the concrete thickness to the thickness of the asphalt. So if I have a 75 millimeter asphalt thickness, this would be the thickness of the concrete for different levels of traffic here on the x-axis. If I have thicker levels of asphalt supporting myself or the pavement, then the required thickness of the concrete's less. Now, the minimum thickness is about 8 centimeters, so that's what the red line here is. You would never design something less than 8 centimeters for bonded concrete overlays. Now, this just shows the graph, the effect of fibers. So if I don't add fibers, here's my thickness versus traffic. If I add, let's say, a little bit of fibers here, this is not very many fibers here. 25% residual strength is about 2.5 kilograms per meter cubed. You can see how the reduction in thickness. You get about an inch reduction if you add about 2.5 to 3 kilograms per meter cubed. This is a great graph to show you the need to have shorter panels for these thin overlays. So if I have 1.2 meter panels, this is the blue line, versus 1.8 versus about 3.7 meters. Okay, so slab size plays a huge role in the thickness design. So we don't want long panels for thin overlays. Well, this is our design method we came up with for the state government. I left the website there, you can look at it. But there's actually another one that's probably more applicable for this country. We helped develop this one for the American Concrete Pavement Association, and it has a design method here with the same equations that we use, but this has a climate file here. Where did it go? Yeah, it has a climate effect here, so you can pick different locations, at least in the US, and you can design the thickness based on the local climate. So this is on the website of the ACPA if you're interested in running a structural design or getting an idea of what thickness requirements you may need. In terms of when should I use these, or some standards here, again, 8 to 15 centimeters, minimum thickness 6.5 centimeters. The state government that I work for, they require fibers when the slabs are around 10 centimeters or less, which most of them tend to be less than 10 centimeters. That's optional when it's greater than 10, but my experience so far says we should be using them probably for all thicknesses. And they limit it to 5 million easels, but we've designed them for slightly higher than 5 million. So they're not exactly designed for 50 or 100 million, but 5 to 10 million is an upper limit for thin overlays. These are just some minimum strength values we use in the structural design. It's probably fairly similar to what you use here in terms of design flexural strengths. The mix designs are fairly similar to what you would use for conventional paving mixes. The water-cement ratio, maybe this is a little low for your country. We have freeze-thaw, so we have to keep the water-cement ratio low. Total cementitious here is pretty standard, and we use about 15 to 20% fly ash in our mixes, type C fly ash. And we basically, in terms of fibers, we use this standard to test the mixes, and we use a minimum of about 1.8. So if you're doing a parking lot, you'd have to use 1.8 kilograms per meter cubed. If you're doing another type of road, you don't want to exceed about 4.5 kilograms per meter cubed. Slab size vary between these values, so we don't get much above 2 meters ever. Just a little bit about joint design. Now, we prefer to have about 1.8 meters slab sizes, and it slightly increases the stress in the slab, but the reason is, this is 1.8 meter here. The reason is if we use 1.2, you tend to have the trucks driving along one of the joints, and that's, we found, not to work very well. So we try to avoid 1.2 meters, especially if you have a lot of truck traffic. If you're on a low volume road with passenger cars, it's not really a problem. In terms of joint cutting, it's fairly conventional. We use a lot of early entry saw cutting with no water. So you don't want to cut too deep, but you need to cut deep enough so the crack propagates. And early entry saws have tended to work very well for HMA or concrete over HMA. This gives an example of a city street that was done with a bonded concrete overlay, and these are the early entry saws. These are dry blades, no water. If you don't cut quick enough, this is an example of what happens. You get a shrinkage crack. So cutting is very important. And you have a lot of joints, so you have to cut early and have enough saws. That's another thing you learn over time. This is a soft cut early entry saw, a more high capacity one. Just a little bit about performance of ultra thin white toppings in my state. These are some projects I visited last year just to see how they were doing. This is one of the first projects we actually did this is 15 years ago. It's still there. It's actually not in very good condition. This was before, it was kind of just put down and see what happens. So kind of the first project. We learned a lot of things. You can see how the slabs are misaligned. It's a very rough ride at this point. It also has the slabs are misaligned here. You can see this joint doesn't match that joint. So with the addition of Fibras, which we started about 2004, you don't see this slab misalignment in general. And the slabs tend to be at the same elevation. So you don't tend to see this type of behavior anymore. That's one of the things we've learned. So that's why Fibras have been an integral part in the decision making. This is another project that was done a while ago before we knew all the things about where to place the joints and the fibers. And again, you can see a lot of cracking. And also these were about 1.2 meter panels, which tended to cause a problem with this. So this is the wheel path, and a lot of trucks run on this road. So we had a lot of damage. So we try to keep the joint out of the wheel path. That's a big deal. So you'd rather have about 1.8 meter slabs than cut it up into 3 different joints in the wheel path. Some of the big successes we've seen is in Chicago, where they've placed these on bus stops where you have rutting problems here. Okay, so you can inlay these on a bus stop. This gives an example of one of the projects. So these are about 10 centimeters thick. They mill the asphalt out here. These aren't that long, about 30 meters long, 30 or 40 meters long. And they put this in one day. They put in about a larger dose of fibers because these have buses, much heavier pounding, and we want to keep all the cracks together. And this gives you an idea. We went up to Chicago last year and surveyed some of these, and still in pretty good shape. I wouldn't say there's no cracks, but with a lot of fibers, these still are being held together pretty nicely. This is a project right outside the city of Chicago near an aggregate quarry. Again, 1.5 meter panels here, 2.4 kilograms of fibers. And this project, after 8 years when we saw it, really no cracking, looks really good. This last project here was done in a very heavy truck traffic route here, and it has a lot more distresses. This actually did have fibers, and this is an embankment. Oops. This is an embankment area, so there is some settling of this roadway, so this is causing some of the problems with this road, irrespective of the overlay. But overall, this looks pretty good. There are some distresses on the road. So one of the things with concrete overlays, especially thin ones like this, again, this isn't that thick, is that the owner has to expect that after a certain number of years, you're going to see cracks. So people generally think concrete shouldn't be cracking ever, or something's wrong. But with overlays, you're going to have some level of cracking because the designs are 15 to 20 years. So you're going to see cracks after 10 years for sure. The question is whether the cracks are going to deteriorate or not, and that's why we add the fibers also. I had the pleasure to go to Uruguay a couple years ago. They were Googling white topping, and they came up, and they emailed me, and I said, well, I'm in Chile right now, so I could come over. And they actually did a pilot study in a neighborhood that no one could find just in case something happened, okay? And they put in a fiber reinforced concrete mix. They milled the asphalt and looked pretty good. The ministry was very happy with the performance. And this is a picture of what happened after that neighborhood white topping or ultra thin white topping. And a year later, they built a 13-kilometer road that had some historical rutting problems because of trucks, forest trucks, and they put 14-centimeter slabs on top of an asphalt pavement there and some fibers and as far as I know, it's working well. No one's said anything to me. Okay, kind of in summary for the bonded concrete overlays, what we're finding is in general, we have very good performance, especially since we started adding our fibers. When we keep the panel sizes around 1.8 meters, this tends to give us pretty good performance, especially when we have trucks. And again, the condition assessment is very important for the success of these projects. If you have bad asphalt or bad subgrade, an overlay is not going to fix it. I'm going to skip this and just go quickly to my last. These are bonded overlays, but that's not applicable. Just a couple notes on unbonded overlays, which are probably less applicable here, but for maybe high volume roads. The key here is that your structural design for unbonded overlays are going to be very thick. They're probably going to be in the order of 20 centimeters for heavy volume roads. So you're going to have to deal with elevation problems with your roadway, bridges, ramps, and shoulders. So unbonded overlays make a lot of sense in the U.S. on rural highways, interstates where you don't have a lot of bridges, you don't have a lot of elevation restrictions with the roadway. When you get into an urban area, unbonded overlays are a little bit more difficult. You have a lot of exits, you have a lot of bridges, and you can't spend all the money raising everything up. So unbonded overlays have a good market, but generally more high volume and rural locations. And the key with an unbonded overlay is you're usually placing it on a really poor surface that has really lost the capacity, either durability problem, too many cracks, and that's, or the agency hasn't rehabilitated early enough. And that happens. We see that in our own state. But you can have unbonded overlays on asphalt also. So you could have a very poor asphalt with a lot of cracks, and you just are not going to assume there's a bond there. Okay, so that would be considered an unbonded overlay, quote, a white topping, but you have to make the assumption that there's no bond there. And we've built some of these. This is white topping projects in Illinois. These are rural roads. Essentially, when you calculate the required slab thickness, you assume there's no bond between the concrete and the asphalt. So this is fairly common to build unbonded white toppings. I'm going to skip this one and just show one last project here. In our state, we generally, there it is. In our state, we generally have high volume interstate truck traffic, and generally we build reinforced concrete slabs on our interstate, and we usually have some kind of asphalt base. Some of the truck routes are heavily truck routes, and it's much cheaper to actually do an overlay than a reconstruction because we don't want to close the road down. So this is just one project in our southern part of our state where we have 42% trucks on a fairly heavy average daily traffic. And in this case, an unbonded overlay, you essentially have an existing roadway, you place a asphalt interlayer or a separation layer of some thickness, and then you build a thicker concrete slab on top of that. Again, this tends to be very thick because you're not getting much contribution from these layers below because they've just degraded enough. So this is about 30 centimeters here, and this is what we call an interstate pavement here. And this had over 100 million easel design. We put steel in our interstate concrete pavements because it provides more smoothness, and that gives us about a 30-year design life. So that's one of the objectives of our unbonded overlays for interstate traffic. This would be an example of an unbonded overlay. This is the asphalt below. It looks white, but it's actually asphalt. This is our steel, our longitudinal steel and transverse steel on our interstate, and this is what the overlay would look like once you're done with it. So this is a high cost item, but this is a road that they don't want to close down for 30 years. It has very little maintenance after this. So the objectives here are much more in terms of no user delays, reduce any type of maintenance because of the heavy traffic. I'm going to here skip to my conclusions because it's getting late here. I'll have to come back to Costa Rica and finish the presentation, Luis. Kind of in summary, as I primarily talked about bonded concrete overlays of asphalt, but the key here again is assessing the condition, so picking bonded versus unbonded, and then finding the structural design method, which may not be that easy, so I recommend going to some of those publications and really reading very carefully which method works. The AASHTO 93 method may or may not work. I would be very nervous using that because there's a lot better tools out there right now. And then make sure you read up on the construction details because your overlay assumptions in the design have to be followed up in terms of the construction details. And if you miss something there or don't communicate, you can have an early failure. In terms of fibers, I think they have a great potential for these thinner overlays, and we've seen their performance right now for about 10 years. It's working well. They increase the slab capacity. They keep cracks tightly together. They hold slabs that are short, the short panels together so that they don't misalign. And they reduce the deterioration rate. So we're going to have cracking on our overlays and because they're thin, and the fibers hold the cracks together. And generally, we can make those economical, but don't add fibers to everything because they won't be economical for every concrete pavement design. And that's my presentation, and hopefully I've saved time for some questions.